Welcome to Fun Photon Physics with Mr. Pyatt. This lesson is on the energy of a photon. Explain what is meant by quantization of energy, define the use of the electron volt as a unit of energy, and carry out an investigation using LEDs to estimate Planck's constant. So, the energy of a photon is directly proportional to its frequency. This constant of proportionality that we can insert here is Planck's constant, which is h, which has a value of 6.6663 times 10 to the minus 34 joules per second. We can insert into this equation the wave speed equation to give us a secondary equation for a photon that gives us wavelength, and this also shows that energy is inversely proportional to wavelength, or lambda. So Planck's constant is this value. In your examination you only need to know it to 3 significant figures. And it was named after the German physicist Max Planck, who theorized that radiation was quantized. What we mean by quantization of energy is that energy has a discrete value. It comes in packets rather than having a continuous potential value. So he called these packets of energy, these quantized amounts of energy, photons. This was similar to the idea that light could exist as a particle that had previously been discussed, but it was unique by adding this quantization. So in quantum physics, we often talk about the energies of photons that are very small, and so in order to do that, we use the electron volt as a convenient unit to compare quantities. So 1 electron volt is the energy change of an electron when it moves through a potential difference of 1 volt. So we should remember from module 2 that energy is equal to the voltage times the charge on an object, and for an electron this equation becomes the energy of an electron that's accelerated through a potential difference will be equal to E, which is the charge on an electron, which is 1.6 times 10 to the minus 19 coulombs, multiplied by the voltage. So to convert between electron volts and joules, we know that 1 electron volt would be 1 volt. In terms of energy, it would be 1 volt times 1.6 times 10 to the minus 19. So 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And so to go this way, you are dividing by 1.6 times 10 to the minus 19. To go that way, you are timesing. So an experiment that we can use to determine Planck's constant then, what we do is we use light emitting diodes, and the way an LED works is that once the LED turns on, it requires a minimum voltage in order to do this. Now the energy that is required to turn this on corresponds to the energy that is lost by the electron, and that's emitted as a photon of light from the LED of a discrete energy level. So if we use this equation, the charge on an electron times the potential difference across the LED, that is equal to the energy lost by the electron. So in effect we can say that for an LED, the minimum voltage for it to work is equal to the wavelength of the energy of the photon that's released, which is obviously also equal to hc over lambda. So the experiment that we do, if we're asked to describe this, is we use a potential divider or a variable power supply. This is obviously a fixed power supply, but we use this to vary the voltage across the LED. So the voltage starts at 0. We use the potential divider to increase the voltage across this until we reach the minimum voltage for this to work. We then record the voltage that's required for this, and we can then use that to calculate the frequency and the wavelength of the light that is being emitted. We can also work out the energy of the photon that's emitted. we can then change the LED for a secondary one. So this is an example that was used in an exam question once, where we have our potential divider. They use this component called a flying lead, which is just a lead that you will only connect it to one of the LEDs at any one time, but you need to do this for different LEDs. So when you do this, if you plot a graph of energy against frequency, if you think about the equations we've done already, the gradient of that, E divided by F, is going to be equal to Planck's constant. So for an energy frequency graph, like the one shown here, the gradient is equal to H, Planck's constant. So the units have to, in order for this to work, the units here have to be in joules, because the units of Planck's constant are joules per second, and frequency has to be in hertz, because 1 hertz is equal to 1 wave per second. And then you can see by plotting the different colours of light on here that as the frequency increases, the energy increases, so we can see our proportional relationship. And because we know that wavelength is inversely proportional to energy, as our energy is increasing, our wavelength is decreasing, which again we can see. So if I plotted a graph of energy against wavelength, then you would get a negative gradient to show that it's inversely proportional. The gradient this time, if we think about the equations that we've been doing, so E is equal to hc over lambda. If you plot a graph of E against lambda, you get your inversely proportional relationship. And so if I divided this side by lambda, I would have a gradient that would be equal to hc divided by lambda squared. If you did a graph of E against 1 over lambda, then E against 1 over lambda, so E divided by 1 over lambda, would be equal to E lambda. And so E divided by 1 over lambda would be equal to E lambda, which is equal to hc. So the gradient of this graph, whilst a straight line and showing the proportional relationship, is a little bit different. Gradient here is now equal to hc as opposed to h. So there is a difference there between these possible graphs that you could have and what their gradient would correspond to. So you should be able to meet each of these objectives now. So you need to be familiar with the two equations, E equals hf and E equals hc over lambda as the energy of a photon. Understand what's meant by quantization as a discrete packet of energy. Apply the quantity an electron volt, and recognise this equation, that the energy of a photon emitted is equal to the charge on an electron times the voltage. And then you should be able to describe the experiment that we can use to determine Planck's constant and how we would determine it using a graph.